Hey guys, welcome to the video on doing a Ka calculation, so using the Ka expression to do a calculation. So one thing first of all, there was a typo on the last sheet. I put the wrong compound in with the wrong concentration. So you can either download the new one or change it to so a student dissolved 1.0 moles of hydrogen nitrite in enough water to make a 1.0 liter solution. What is the pH of the solution? So it's 1.0 moles of hydrogen nitrite. So I've written out the equation. I've calculated out my concentration of the hydrogen nitrite. Then I've made my basic ice table. So I got my compound. So I have hydrogen nitrite dissolved in water, which is now nitrous acid, the hydronium ion, and the nitrite ion. Then I have Ci, delta C, CeQ, 1.0, 0, and 0. So take a moment, perhaps pause the video, and get those values down for yourself. Okay, so now that we have that, taking a look at our equation, we don't know how much hydronium HNO2 is going to make. If it were a strong acid, since we have 1.0 moles per liter of HNO2, it would make 1.0 moles per liter hydronium. We could just use stoichiometry and a mole-to-mole ratio. But since, instead, it's a weak acid, and we know it doesn't ionize very much, we need to make an ice table, and using our Ka expression, determine how much hydronium is made. So we know we started with 1.0, 0, and 0. How much does he lose? We don't know, so we'll call that minus x. How much does these guys gain? Do they gain? We don't know, but since it's a 1-to-1 relationship, and a 1-to-1 relationship, if he loses x, they each gain x. So we add the two rows together. So at equilibrium, we have 1.0 minus x, x, and x. Hope you guys can see that. I'll move my head so we get the sign there. So 1.0 minus x, x, and x. Sorry, I kind of need the light on there. Okay, now, if we go ahead and do our Ka expression, which I'll set up over here, so just like you guys did in equilibrium, you go ahead and you put your products over reactants. Again, if you want to practice it before seeing what I have, feel free to pause the video for a moment. So we go Ka equals the concentration of hydronium times the concentration of the nitrite ion, which is the conjugate base of hydrogen, the nitrous acid, and all over top of the nitrous acid, which was hydrogen nitrite added to water. Water is not part of the equilibrium because it's a liquid. So there is my Ka expression. Now, if I were to go ahead and substitute these values in, I would not have a perfect square, and I would have to go ahead and use the quadratic equation. Let's go ahead and try the assumption to see if we can get rid of this x here if it's too small. So we take 1.0 moles per liter, which is the initial concentration of our acid. We divide it by the Ka of the acid, and my chart says 5.6 times 10 to the minus 4. And when I calculate that, I get about 1700, which is greater than 1000. Therefore, the x value is small enough that when we round it to two significant digits, it'll still be 1.0. So I can go, therefore, CeQ equals 1.0 mole per liter. So the change will be so little, it'll still appear to be 1.0 mole per liter with two significant digits. Now, I can take this, instead of this value, because I've now redefined it, I can take this value, and this value, and put them into my ice table. I'll also put the Ka in. So there's my substitution. Now, I I do some algebra, so I multiply both sides by 1.0. So I get 5.6 times 10 to the minus 4 is equal to x squared. And when I square root both sides, I will get my answer. Hang on a second here. I need to figure out how to get a square root with my device here. Oh, there's a calculator. So 0.00056 square root, and I get 0.0236. So x equals 0.24 moles as a value. We know that since here in the chart is moles per liter, this will be 0.224 moles per liter. Oh, sorry, 0.024. So I know that my x value here is 0.024, this x value is 0.024, and this x value would be 0.024, and if I were to subtract it from 1.0, it would still round to 1.0. So now I haven't actually solved the question yet because it says, what is the pH of the solution? I now have a hydronium value, so I can declare that H3O plus equals 0.024 mole per liter. Now, what I need to do next is I need to go ahead and using that get a pH. So I'll put my pH formula down. pH equals negative log H3O plus, which is negative log. Now, even though I'm going to write that number down, I keep the real number in my calculator. Use a round bracket, 0.023664. I'm going to put extra digits here. And I put units. You could just write down 0.024 as long as you use the correct number from your calculator. Now, let's try this. Okay, I think this is the answer. I think if this calculator worked right, if not, hopefully yours worked better. I've got 1.63 times 10, or 1.63, sorry, as a pH. That sounds about right. So please do your calculation. I'm using like a cell phone calculator, so I'm not sure if I've used it correctly, but it looks like it's a correct value. So to go back, the steps, first of all, you take your information, and it says we have 1.0 moles of hydrogen nitrite dissolved in enough water to make a 1 liter solution. So I use that to get my concentration of the HNO2. I write out my equation. HNO2 plus liquid water makes hydronium and nitrite. Then I make an ice table to gather my data. HNO2 concentration, hydronium concentration, nitrite ion concentration, which is the conjugate base of my acid. I have CI, my initial concentration is 1.0, 0, and 0. The change in concentration, delta C, is minus X, plus X, and plus X. Why? Because it's a 1-to-1 mole-to-mole ratio. So then I add these two rows together, and at equilibrium I have 1.0 minus X, X, and X. Now, if I use this value, I will end up having to do the quadratic. I don't want to do the quadratic, so I will try the assumption. So I take the initial concentration divided by the Ka value from the data book, and it is greater than 1,000, so therefore I can redefine my equilibrium value as 1.0 moles per liter. So then I take my balanced equation, make a Ka expression, so my product concentrations over top of the reactant concentration, excluding liquid water. Then I substitute in my values. So 5.6 times 10 to the minus 4, which is the Ka, x and x from my chart. And I substitute in the 1.0, which I redefine my equilibrium value as. And then I go ahead and do some algebra. So I get the 1.0 at the bottom, so I multiply both sides by it. Then I square root both sides, and I get x is 0.024. That is now my concentration of the hydronium. Oh, I should put brackets there. Now that I have that, I can put my pH formula down. So negative log of hydronium. Plug in my numbers with units, keeping the real number from my calculator, not the 0.024. And it looks like I get a pH of 1.63. That is how you'd go about solving a calculation for Ka, using the assumption, and continuing on all the way to end it to pH. All right. Next video will be a Kb video.